In his 1937 paper on computable numbers, Turing considered the problem of determining what sequences of symbols the machine could produce. For example, could the machine produce a tape with a sequence where the kth one is followed by k blank spaces? Turing gave the first description of what is now called a Turing machine. His description is slightly different, but in modern terms we usually phrase it this way. A Turing machine is a 5-tuple where Q is a finite set of states, not including some special state H called the halt state. Sigma is a finite set of symbols called the input alphabet. Gamma is a finite set of symbols not including the blank symbol called the tape alphabet, where sigma is presumed to be some subset of gamma. We have some state Q0, our initial state, and delta is some function not necessarily defined for all inputs from the set of states and the tape symbols, including the blank symbol, to the set of states together with the halt states, the set of symbols together with the blank symbol, and the set right, left, or stay in place. Now, the definition of delta seems a little complex, so let's take it apart. Delta has two inputs, a state from Q and a symbol from the tape alphabet, or the blank symbol delta. It also has three outputs, a state from Q, or the halt state H, a symbol from the tape alphabet, or the blank symbol, and a direction to move the tape head right, left, or stay in place. So, suppose delta of Q gamma is Q prime, gamma prime, X. And so the Turing machine is in state Q and reads symbol gamma. It will change its state to Q prime, change the symbol to gamma prime, and move left, right, or stay in place. And to make things easy, we'll assume that it does it in that order. So keeping track of what everything is, Q is the current state, gamma is the current tape symbol, Q prime is a new state, which might be the halt state, gamma prime is a symbol that will replace the current symbol, and X is going to be whether the Turing machine moves to the right, left, or stays in its current location. Now, notice that since the halt state is not considered one of the state, delta of H gamma is undefined. So if delta ever changes the state to that halt state, the Turing machine will halt at that point. It will not process any further input. Also note that, for now, Turing machines are deterministic. Delta of Q gamma has a unique output, Q prime gamma prime X. And we'll refer to this transition as a move. So for example, let's find the moves given our delta transition function. Note that when describing our moves, we put them in the order new state, new tape symbol, and tape head movement. So let's read our transition function. If the state is Q0 and the tape symbol is delta, the blank symbol, we move right. Since no state change is indicated, the state remains Q0. And since no symbol is printed, the tape symbol remains the blank symbol. So delta of Q0 blank is Q0 blank R. Meanwhile, if the state is Q0, the tape symbol is 1, we move right and change the state to Q1. But since no symbol is printed, the tape symbol remains 1. Next, if you're in state Q1, if the symbol is the blank symbol, you change state to Q2, you keep the current symbol, and move right. But if the symbol is 1, you keep the current state, the current symbol, and move right. If you're in state Q2, the tape symbol blank changes you to state Q2, the tape symbol remains blank, and you move right. The tape symbol 1 changes you to state Q3, prints a blank, and stays in place. Similarly for the states Q3 and Q4. Now, given a Turing machine, its configuration at any time is defined by three things: its current state, the tape contents, and the current location of the tape head. We'll describe this as where Q is the current state, X is the portion of the tape to the left of the tape head, A is the symbol at the current position of the tape head, and Y is the portion of the tape to the left of the tape head. The other left, the one that's on the right. Now, as written, A is going to be a single symbol of the tape alphabet, but under some considerations we might consider that to be some string of symbols of the tape alphabet, and in that case we'll just take the tape head to be at the initial symbol of the string. So for example, let's consider the Turing machine shown and let's describe the configuration. So we see that the Turing machine is in state Q2. The current symbol is 1. The preceding symbols, the symbols to the left, are, and the symbols to the other left are, and here we're assuming that all the remaining tape squares are blank, and so we can describe our configuration as. Now suppose the machine uses the move delta QA, Q prime, A prime, X. Then the state is changed to Q prime, the current symbol is changed to A prime, and the tape head has possibly moved. We might write this as, but we'd be wrong. Since we might move, the symbol A prime might no longer be at the current symbol. So we should write, and we'll use the notation to indicate that our machine moves from this state and this tape to a new state with a new tape, and we say that this indicates that Q, X, A, Y derives Q prime, X prime, alpha, Y prime in one move. And this notation to indicate that we've derived it after K moves, and this notation to indicate we've derived it after some finite number of moves, possibly including no moves at all. So suppose we let our Turing machine make one move. We can try to describe the new state, and we see that our move was to change the state to Q3, erase the symbol, in other words, we printed delta, and we didn't move, so our new configuration is, and we'd write that our initial position derives the new position in one move. And if we let our Turing machine run, we'd eventually get to some state Q1, where our tape looked like this, and so we could write from our position, we eventually get to this position.